Okay, so there are two things I want to recap.
The class? Should I just move it to next week?
So the first thing is that the name universal hashing family, although the name is like universal, is a weak thing. Okay, like it's way weaker than the ideal hash function. It's just the one such like this name universal just means that it has small collision properties, meaning that if you sample a function from this family H, which is a weak one, it just guarantees this thing. Instead of n-wise independent, which is satisfied by the ideal hash function, it just satisfies this simple thing. And that's what universal means. So don't let the name trick you to think that it's strong. And I talked about this construction of universal hashing family, and I make some mistake in the calculation, and I update this calculation thanks to Daniel who pointed out. So you can look it up and see how it works, but morally it's the same kind of thing, but it's just some miscalculation. Okay, so you can look it up later. And today we're gonna talk about more hashing algorithm. So again, right? What we want to do is we want a dictionary with just 3 operations. You can update and delete dictionary, and you can look up whether an element is in a set. And also the universe is bounded, just like before, just like last time. The universe is bounded by some number, u. U is a huge number, but it's still bounded. Okay, and like last time, when we design hashing algorithm, what we do is we design, just design and analyze algorithm. That first, just assume that you have a completely random function, or the ideal hash function. And then once you have analyzed that, then you just see that, okay, maybe you can just replace it by a simpler hashing family. And from the last time, we just said that, okay, just replace this class of all function, and when you sample, you get the ideal hash function. You just replace it by hashing family with a small collision property, namely universal one. Okay, so that's what we get last time. We get that instead of log n query time, you can get constant expected query time. And now today the goal is to actually make this thing worst case. And we're gonna go through this one by one. The first one is called one level perfect hashing. So this one is extremely simple. It's just one step. Let's say you have n keys. So the only step is just to choose a random function such that it maps u to n squared instead of n. So it takes quite a big space, it's n squared. But that's it. That's the only thing we do. Okay. And now let's see what happened. Well, we said that x and y, let's say x and y collide if h map x and y to the same place, right? If x and y are different but they map to the same place, then we said they collide. And as before, x and y would collide with probably at most 1 over m. And this is true for universal hash family too, but yeah, we have ideal hash functions, so this is true for sure. So now that each of them collide with super small probability, because now we set m to be just n squared, what do you think is the expected number of collision? So we can just calculate it, right? How to do that? Well, we just say that, okay, this is just a sum of all pairs x, y. Maybe say this. What is collision? It's just a sum of all pairs x, y, such that the indicator that x and y collide. Right? And then by linearity of expectation, then you put the expectation inside and of this thing, x and y collide. But that is just what? Just the probability that x and y collide. Okay. So how large is this? Anyone?
Yeah, plus one.
Maybe less than 1, actually. Because, okay, it's true that this thing is n square, at most n square here. But how many guys are in the sum? Just n choose 2. Yeah, so that's like at most 1/2. Okay. So now that we have that this is at most 1/2, then what do you think is the probability that there exists collision at all, or the probability that the number of collision is at least 1? What is that? Can you bound this to? It should be less than 1. What should we use it? What should we use to bound this thing? So we know the expectation of collision now, and the distance is less than 1. It's like at most half. So now I want to say that the probability that is actually at least 1, so more than half. What should this thing be? Like, or what bound we should use? Okay.
Markov.
Yeah, Markov. And what do you get from that?
Memory serve is supposed to be 1 or 2.
Yeah, it's just the expectation over 1, which is this guy. But that's just at most, this is now at most 1/2. Right. So now we have that when M is this big, the probability that there exists any collision at all is just at most 1/2. So like with probably at least half, right? Nothing collide. And if nothing collide, then that's great. So yeah, we get that there is a collision with probably at most half. So now, if you have some hashing and nothing collide, right? It means what? It means that you can look up in just constant time. Just like evaluate the hashing, evaluate a hash function, go to that place and check if it's there. So, and note that here, instead of using ideal hash function, we can use universal hash family just because the only thing that we need in the analysis before is just this thing. But that is just a thing that is certified by universal hash family as well. So we can just use, just sample, instead of use the ideal hash function, just sample a function from universal hash family, right? So now the algorithm would be, okay, just sample a function from the universal hashing family, and if there's no collision, then you're done. And if not, then you try again. Right. So now I claim that the number of repetition is just 2. You don't need to repeat too many times. So why is that? It should be very intuitive. Like you don't need to say like why 2 exactly, but why you should stop after a few times.
Well, if the probability of there being a collision is just 1/2, then basically like the expected number that you need to do is like the inverse of that, which is 2.
Yeah, exactly. So it's like just imagine the process where like on each trial you would succeed with probability half, right? If you ask how many times you need to repeat until you succeed, this is exactly what geometric distribution is. Like just try to count the number of times you need to try until you succeed. Here the success probability is at least half. So the expected time of repetition is just inverse of this thing, which is 2. Okay. So yeah, so you see like we just need to repeat in the expectation constant time, and then what we get is a dictionary with space n squared, which is too big, like not that good. But the query time is just constant just because there is no collision. And but here at least it's not that clear how to support update, insert and delete. Because you see, here we try to resample hash function as long as there is no collision with respect to S, with respect to your set. But now if you update your set, then after some updates, you might have a collision in it again. So, and maybe you need to retry and it's not clear, like maybe you need to retry like after each update. So that's why like here we don't support updates, but at least it has really good query time. Okay. Question about this?
Sorry, you say it didn't support update?
Yeah, we don't support update. Yeah.
Oh. Can you repeat the reason?
Well, because here, like, we don't want any collision, and there's no collision with respect to this set. If now the set change, there might be again collision, and you need to retry. Okay, good. So now that, okay, this is n squared, it's too big, we want to fix this. So now the idea is actually similar, that now it's 2-level perfect hashing. And to talk about this, I want to recap hashing with chaining, right? So here, like, we just said that we will allocate the array, and let's say it's of size n, right? And here when you allocate array of size just n, okay, there might be some collision. And if some key collide, you just put them into the same list, into the list. That's what we did last time. But last time we said that, okay, if M is n, at least the expected length of the list is constant. But that's just in expectation. So the time to scan through the list in expectation is constant. But we don't like this expectation thing. So now the idea is this. Instead of using the list, can I just replace each list with a one-level perfect hashing that we just seen? Okay. So that's the idea. So the picture is gonna look something like this, and let me explain it step by step, the algorithm. The first step is just pick an ideal hash function, but now you allocate only n entries instead of n squared. And then, so this is like the first array here. It's n many guys here. So, and you know that like once you allocate array of size n, okay, there might be some collision when you hash the set using this first level hashing. And now what I define is, let's say that Si is just all the key that is mapped to position I. And let's say that Ni is just the size of Si. Now, so for example, this thing have size 3. So Ni of this is 3. So what we do is just basically for each of this set, right? Just pick an ideal hash function, hi, that map this set Si to this size array, the array of this size, Ni squared. So this is just like a one level perfect hashing here, right? This is just what we did. And we know that at least if you try like twice, then this guy will map, like will have no collision with respect to Si. Question?
So basically just hashing twice?
Yeah. So know that there is one function here, and then you create a bunch of function hi. That kind of map again. Yeah. So in first level there is one function, but in the second level there are many functions. But you know that if Si is of size Ni, then at least Hi here should map Si with no collision. If you just try twice. So let's assume that there is no collision on Si. Okay, and that's it. So now for each of this array, like that you allocate for Hi, you can append the array of Hi into one array A, and put it here. For example, if in the first position here there is nothing, so it allocates 0 cells in A. And then if this guy have three keys in this position, then you would allocate 9 cells in A. And here you allocate just 1 in A. Okay. And here you know that for each of this allocation, for each position here, you have no collision because you use perfect hashing with one level. So yeah, so basically you see to look up, you just need 2 hash function evaluations. And if you assume that you evaluate this in constant time, so that's constant time. Now, what is the space, right? So the space is clearly n for the first array, and then it's just a sum of ni squared for the second array. Now, I claim that this sum, is just linear in expectation. So, but we will see why in the next slide. But is this algorithm clear? Question about this algorithm, except why the space is linear. Okay, is it good? Okay. So all I need to do is just try to compute the expectation of this thing, right? Because this n is just n, like there is nothing random about this. Just need to compute the expectation of the sum of ni squared. So let's do that. That's the claim. So what do we have? Let's, from the definition of collision, right? Collision is just it's just a sum over all position, and for each position, how many collisions are there in the position I is n I choose 2. For example, this one, it gives you 3 collisions because this pair collide, this pair collide, and this pair collide. So that's the number of collisions, which is basically in order of n, sum of ni squared. But we know that the expectation of collision is just n, right? At least actually n over 2, but yeah, doesn't matter. So this just follow from, like we know, we have seen this before in hashing with chaining already, but we can try to look at this again, right? Well, what's the expectation of collision? Well, there are like n choose 2 pairs of keys. Each pair, they collide with this probability. So that's why it's at most n. Like n choose 2 over m when m is 1 over n. So that's at most n. At most n. So would this mean what? It means that this thing, the sum of ni squared, which is exactly collision, in expectation is at most n. So we get this. The expectation of sum of ni squared is at most n. So that's why this thing is n in expectation. So we are almost done, except there is something that is like we need to deal with. What is that last step? Well, it's because we use the ideal hash function. Right? We don't want that because it's inefficient. So we would just replace it with universal hashing family again. And why is it enough? Right? The reason is, well, this thing, this is just exactly one level perfect hashing, and we saw before that it works for, like we can just use universal hashing family. How about this one? Can anyone tell me why you can replace this guy with a random function from universal hashing family?
The property that you depend on is the less than or equal to 1 over m.
Yeah, exactly. Like when we look at the property, why did we use this thing at all? This is so that the space here in expectation is at most n. But if you look at this analysis, right, this is where we need this. Like this is the only property of hash function that we use is here. That is the thing that is exactly certified by universal hashing family. We just need this thing. So because this property is enough for us throughout this analysis. So let's just use universal hashing family instead. So now we just replace everything that is ideal hash function with this green thing. So that's it. So that's what we get. We get a two-level perfect hashing with constant query time, and the space is linear in expectation. And again, we don't support update because you see, like we kind of sample HI so that it has no collision with respect to the current set, to the current fixed set. So we don't support update. There is a way to make it support update, but it's not that nice. One question. There is an easy trick to remove this to make it worst case. Instead of linear space in expectation. So what do you think? Like, do you have some like guess how we should make this worst case? There is a simple trick to do this actually.
For the top level hash function, could you keep re-rolling it until you get one that doesn't have linear collisions?
Yeah.
Like that?
Yeah. Something like that. So the idea is actually more generic. Like this is a trick that kind of very generic and you can reuse this many times. So let me explain. So we know what? We know that the expected space is linear. So let's say it is like Cn for some C. So now, what is the probability that when you do the whole thing and you get that the space is actually more than C to Cn? Yeah, tell me. What is this? We have anyone? What should I use? You answer. Sorry? 1 over 2. Yeah, thanks. What did you use? How did you bound this thing? Markov?
Markov.
Yeah, exactly. Thanks. Yeah, we're gonna use Markov again and again, so you better remember this. But yeah, you see, like you bound expectation, it deviates from expectation by 2. Just use Markov. So now you know that okay, the probability that it takes more than 2Cn is at most half. Okay, so what I'm gonna do is I just try to implement this perfect hashing. If it takes the space less than 2Cn, that's still linear, right? So I'm good. But if it takes more than 2Cn space, that only happens with probability at most half. So how many times I should retry in expectation? Just 2 again, right? So just try to redo this again and again, not too many times. you can now make this thing worst case. But you kind of put the expectation into your construction time, right? Because now like the construction time, you you keep redoing until you get a good space. It's true that the construction time in expectation is good, but anyway, you construct it only once. So good. So now that's it for two-level perfect hashing. Next, I'm gonna go to Cuckoo hashing. So this one is the one that is clear that you take ON space and constant query time. It also support update and also it works very nicely in practice. So let's go there. So Cuckoo hashing. Again, let's say that n is the upper bound of keys that we're gonna handle ever. Like you can handle update, but it never be more than n. So now what I'm gonna do is I choose two hash function, the ideal one. Okay, h1 and h2. And I would allocate, let's say 6n for each 6n entries for each function. So I have two arrays, A1 and A2. And what the invariant I'm gonna have is that for each key x, right? X should be either in array 1 on position that like x is either in A1 in this position that hi of h1 of x, or is in this array 2 at the position h2 of x, but not both. So for example, I have a key C, and let's say that this is where like h1 of C map to, and this is h2 of C. Okay. And now we need that C must be in one of these places. And if we have this invariant, then the lookup time is super simple. Just look at the two places that it can be, check if it's there or not. And to delete, just do the same. Look at the two places that it can be. If it's there, you delete it. And the hard part is how to insert. Okay, how do we handle insert? So let me describe how to do that. The first attempt, which is not quite right yet, is this. What I'm gonna do is I just gonna insert x, like look at the place where x should be, and swap whatever is there, like just put x there and swap it with x. And if x is null, that is this used to be null. Now you swap and x is null. Now if x is null, that now you're good. You successfully put x into the blank space. But otherwise, you would kind of repeat the swap. And you repeat the swap, and you also try in other place. Maybe let me like let's see the illustration. That's much clearer. Suppose that like A, B, C, D, E, F are in the table, and like this. And then so each of it, like each is in the spot that is hashed into A1 and A2. Like E is here in A2. So now suppose that I insert X, okay? And for simplicity, let's say that both H1 and H2 map X to 0. So X is here, it's mapped to both of these. So what I'm gonna do is that I'm just gonna like swap X with A. Like look at where X should be in A1. Just swap X with this guy. So X just kick A out. And now A is out of its spot. What you do next? A will try to kick someone again out. So A just kick D out. And okay, D is out. So you try to kick, like D wanna kick someone, so it kicks C out. And you keep kicking someone. Like C now should go to E. E is now out. And now E can go to some place. E just put it there. It doesn't need to kick anyone because no one is there. So once you successfully put it into some place, then you're done. Okay. So, make sense? And so actually it can be something like this too. That is, suppose that, maybe actually, let me ask you, what could go wrong? Yeah. Something super bad can happen. Okay.
Can we have like a cycle of dependencies where we never find a place for everything?
Yeah, exactly. So it can be the case that you can have keep kicking someone and then like it's just infinite, like it just run infinitely. So that's not good. So now there is a simple way to do this, to handle this. So suppose now that, okay, suppose you have loop like for 2n times, and now you know that, okay, if you have loop for 2n times, then there must be some like infinite loop going on. Like you know for sure that you will not ever stop. So if you know this, how we're gonna handle this is extremely stupid. Just redo everything. So just rehash. Just choose the hash function again, h1 and h2, sample it again, and reinsert everything from scratch. And hope that this time nothing gonna be bad. Like, you're gonna be like you want like a run infinitely. Okay. So you see now like the space is clearly linear. Look up and insert. The lookup is constant. Deletion is constant. The only thing we need to analyze is the insertion time. Because you might need to rehash and do again and rehash again and rehash again. How bad can this be? Right? So the claim is that this insertion time is going to be constant in expectation amortized. So both amortized and expectation. So let's see why is this. So let's analyze it. The way to analyze this is we will look at some graph. It's called Cuckoo graph. And Cuckoo graph is just this, like it's a graph with vertex v and he, such that each vertex, like this vertex set correspond to the entries of array. So these are the nodes of the graph, right? There are two sides, and the edge for each the edge is like this. Like we define like this for each key x. Okay? You just create an edge that connect h1 of x and h2 of x. So for example, this is an edge for the key. So there will be like 12n nodes because each of these have 6n nodes. But the number of edges is small, like smaller than the number of nodes here, just n at most. So now let's try to like try to analyze what it means by like when we rehash, what it means in the language of graph, of this graph, Cuckoo graph. So let's consider when you insert x, right? Like suppose you have some graph. This is a graph that I just defined. You have some graph. There are some edge here and there. There might be some circle. Then now I insert an edge. Maybe it's an edge here, like maybe like this. Ex. Then I will let like a cc of x be the connected component of ex. So now this one gonna be ccx. So if I insert an edge here, then this whole thing gonna be ccx. So it's just a connected component of an edge after I insert. So now suppose that when you insert x, and if cc of x has at most one cycle, then I claim that there's going to be no rehash. And if cc of x contains more than one cycle, then there's going to be a rehash. So this is a characterization of whether you will rehash or not. So let's see some illustration, right? You can prove it, but so suppose that maybe the hardest case look like this, okay? And maybe suppose that I insert this e. This is ex. Okay. So maybe in the beginning there are keys like this. A is here, B is here, C is here, D is here, E is here, and maybe this Z and Y. So the number of keys will be the same as the number of edges, right? Here there are 2 edges, so there will be 2 keys. Y can be, let's say this is EY, this is EZ. Y can need to be somewhere, either this or this, but Y is here and Z is here. That's how it's like. And here X, A is here, B, this is EA, EB, and so on. Yeah. So suppose that this is our current array. Suppose it looks like this. So now, suppose that I add an edge, ex. So E need to be somewhere, either here or here, right? So suppose that I claim that there's gonna be no infinite loop, although there is a cycle. So if it's clear that if I want to push x to this place, x would push z, z then would push y, and y would be here. Then you are done, right? I insert x. Let's say I want x to be here. So now, let me use different color. X should be here. X is here. Now c is here, and now y is here. C is here, now Y is here. So then you would be done. But what about I kind of choose it in a stupid way? I want to choose X to go in this way. So let's see what happened, right? Well, X would go here, and then it would push A. A would want to be here now. And now B would be here, and C would be pushing to here, which push D here. But D would now push D would be here, and E would be pushed, and it would kick B out again, right? Now E is here, B is now here.
I think that should be A.
Oh shoot, right. Thanks. Good. Yeah. Is A is here. E now wanna kick A out. Thanks. Now E would be here. And now A come back here again. Which push X back to the good place. And now everything keep pushing until Y is here. Okay. So, but you see, like, as long as there is only one cycle, you might, like, in the worst case, like, if there is one cycle like this, you might, like, and let's say it's like this, and when you want to push X in this way, you might keep pushing, but it will keep pushing back, and then you will be good at the end. On the other hand, if there are two cycles, now things get really bad, right? Because okay, you kind of, if suppose that I insert X, which is I insert X, and let's say this is my new edge of EX, and I push X, and it will keep pushing and push back, but this guy pushing and push back and so on. So that's bad. If you have like the minimal graph that with two cycle can look like this, like two cycle connected by the path. We call it dumbbell, or like a coffee cup, which is one cycle and with like one path like this. If you have this kind of thing, you will like run infinitely again. You can try to check, but yeah, I hope this illustration like convinced you that this is a characterization of rehash. Okay. So now, so what we wanted to say is that it's hard to have this kind of configuration. When you insert n guys into your array, like insert this n edges into the graph, you shouldn't get this kind of subgraph. There's no component with two cycle. All we need to do is this. Okay, so to prove this, I need one key lemma. And the lemma is as follows. So suppose that R is at least 12n, which is the case. That's how we set R. Now, for any node I and j, any position ij, I say that the probability that there exists a non-empty shortest path from I to j, and that path have length n, is something like 3 to the minus L, of length L. That probability is like 3 to the minus L over R. So think of R as something like, R is something like linear, right? So this is like 1 over n, and also like it's at most 1 over n, and also it kind of grow, like shrink exponentially in the length of the path. This probability is kind of, when L is large, then this guy kind of shrink rapidly. So we're gonna prove this soon, but let's say that once we have, suppose that we have this claim, then we can bound a bunch of things that looks like useful for us. Okay. So let's try to do this together. So if let's try to say that what's the probability that I and j are connected, right? This is just the probability that for some L, right, there is a shortest path from I to j of length L. If it's connected, there must be some shortest path of some length. So now can you bound this thing? So the bound is just to use union bound because this is like for sum j. So I want to instead like now just summing over all for sum L. Yeah. Now I use union bound and just summing over all L such that this probability there is the shortest path, exists shortest path I to j of length L. Right. And that thing we know from the key lemma, which is now is sum over L, 3 minus L over R. And we can calculate this, and this is just geometric sum, which is 1 over 2R. Make sense? Okay. So now, what about this? What is the expected size of a connected component of I? For each node I, what is the expected size of this component? Well, we can use like a linearity of expectation, right? So sum over all j, and this is just the expectation that indicate that I and j connected. This is just linearity of expectation. Because the size of the CCI is just sum over all this indicator. Right? So what is this? So J range from 1 to R, right? That's the number of nodes. So what is this? Anyone? Yeah.
1/2.
Exactly. It's at most 1/2 because there are R nodes, and each of these things, this is just the probability that I and J are connected, which is 1 over 2R. This is 1/2. Okay. What about this? What's the probability that I is in a cycle? Well, if I is in a cycle of length, L, then, and suppose there is no shorter cycle, like there is, every other cycle kind of is longer, okay? If I is in this cycle, it means that the shortest path, the shortest non-empty path from I to I is of length L. This is why I want to talk about non-empty path, so that I can talk about cycle of I. So it means what? It means that this thing, the probability here is just the probability that there exists some L such that the shortest path from I to I is of length L. For some L. Right? But now we can bound this in the same way like we did for here. So just use union bound and apply the key lemma, and so we get that this is at most 1 over 2R. Okay. Just do the same thing here. How about the probability that there exists cycle? What it should be? Okay.
The sum over all I that I is in a cycle.
Yeah, sum over all I that I is in the cycle. So that's gonna be, so that's union bound, and so sum over all I, which is there are many of them. The probability that I is in the cycle is at most 1/2R. So this is again 1/2. So now with this, now you should smile now, because like things you will rehash with when there is like a component with 2 cycles. But after you have n insertion, right? After you have n insertion, the probability that there is a cycle at all, not just the component with 2 cycles, that this probability is actually small, like one half. Okay. So let's try to exploit this file that we have derived, right? Okay. So suppose that we have done n insertion. We're gonna look at total time after n insertion. That's why at the end we will get like amortized time. So imagine that you have insert n times. So if you insert n times, then there are like at most like R is still bigger than 12n. So okay, this is 12n. So the lemma actually, yeah. So the key lemma applies, and we know that the expectation of each connected component is at most half, and even after n insertion, the probability that there is a cycle is at most half too. Okay. So now let's look at the time that we need to rehash, right? So you know that if you rehash, there must be a component with 2 cycles. So there must, in particular, there must exist a cycle. So the probability that you're gonna rehash k times is like at most the probability that there exists a cycle after you redo everything k times. So that's like the probability that you got a cycle to the k. So that's at most 1/2 to the k. So which means that in expectation, the number of rehash is just constant. Actually, you can just say that the number of rehash follow again geometric distribution, and you succeed with probably at least half. So in expectation, you rehash at most like just 2. Okay, so now how about insert? Each insertion takes time proportion to the size of its connected component. Right? We saw before that, okay, in the bad case where you kind of insert, and like when you insert here, you might kind of walk through this connected component, like some node, you might walk through it twice, but it's always at most twice. So the time that you keep kicking things is just the number of swap is proportional to the size of the connected component that you add of EX. But any connected component is of size in expectation is just half. So that's constant too. Good. So now it means what? It means that in expectation, the total time that you're gonna do is just the number of insert. Each of them, you spend constant time in expectation, plus the number of rehash. And if you rehash, you're gonna need to reinsert everything in n time. So that's like O(n). But you're gonna rehash just constant times in expectation. So in total, that's n. So that's expected total time is n. It means that the expected amortized time is constant because this is time after n insertion. Total time after n insertion is n in expectation. So expected amortized time is constant. All right. Question about this?
Why 12?
You will see now in the proof of key lemma. More question. Okay, so let's prove the key lemma. So this is what we want to prove, right? We want to analyze the probability that there exists a non-empty shortest path from I to j of length L. So let's prove by induction on L. So when L is 1, if there is a shortest path from I to j of length 1, it just means that there is an edge from I to j. So what is the probability that there is an edge from I to j? It means that there exists a key x, right, where this thing is I and this thing is j. So how should we analyze this? We see this thing in the bound, so we use union bound again, right? By union bound, we get that it's just a sum over all x, this probability, this thing here. What's the probability that this guy maps to I and this guy maps to j? So what is this? Well, there are array here. This is of size 2r over 2. This is r over 2. So this thing, if the function is random, then this is just 1 over r over 2 square. And there are n many keys here, so it's n. Right. So that's because you set r to be bigger than 12n, so that's at most. So what is this? Like this is 4n over r squared, so that's at most 1 over 3r. I'm sorry, did you? Yeah. So maybe I write it here. Sorry. This thing is just 4n over r squared, which is 1 over 3r. Okay, so that's simple. So now that's the base case. So now let's do the general case. So this is the case where we have when there is like shortest path of length L, right, from I to j. It means that for some k, there must exist the shortest path from I to k of length L minus 1, and then there is an edge from k to j. So there's a path of length L from I to j, so there must be some guys k here. This is of length L, this is of length 1. Okay. So now, what's the probability that the first event happened? The first event, you can bound this just by induction, right? This is just, we have, just by induction, you get that the first event here is at most L minus 1 over R. So now, I just need to analyze the second event. But So okay. So what I want to analyze at the end is like you see, maybe I just analyze this. What's the probability that the second event happen given that the first event happened? Because if I bound this, then I get the bound that like the first event and the second event happen. If I can bound both of these. So now you see this second event here is just similar to what we have done before, right? It's just bounding the probability that there is an edge. But now we know a bit more. We know some more information. And it would be bad for us, actually. We wouldn't be able to bound this if this path contains this edge, j, kj, right? Because if this path exists and it contains an edge kj, then it means that this event will happen with probability 1. But that just cannot happen. This is the shortest path. Just connect from I to k. This guy wouldn't contain this edge, right? Because this is the shortest path. So you know that, okay, there are some edges that is there. It's disjoint from this edge. So this is actually even better for us. You know that there is a lot of edges out there, which is not this edge. So the probability that there is this edge. Now you can just do what? Like, kind of, it's just the same thing like before, which is at most 1/3R. So in particular, when I do this union bound, right? Here I just analyze that there is an edge or not. When I do union bound, here I do overall keys. But if I want to analyze this now, I don't need to union bound over the keys that are in this path. I get even better bound. So, but the intuition is just that, okay, you know that there are a lot of edges out there. So there is even less key that you need to union bound over. So you get this. It's just the same analysis. Question about this? Okay. So now, what we have is this, right? We have that. Now we can bound this, like this probability. What we want here is just a sum over k. We use union bound again. Sum over k, and the probability that like event I happen times like event I maybe and event 2 4k happen. But that is just probably that event 1 times event 2 given event 1 happen. Right? So you have this thing, which is here. You have this thing, which is this. And so what you get is like, maybe I just put it here. You have this and this. Summing over k. There are k nodes. There are r nodes. And this term is just this thing. This term is here. And you get this bound. So that basically complete the analysis. question about this analysis before I move on?
So R here is a number of nodes. Isn't N the number of nodes?
No, n is the number of edges. Like normally I use n for number of nodes in previous class, but here n is the number of edges. N is the number of keys. Key is an edge in this graph. Each key is an edge in this graph. Okay. More question? Okay, so you see we kind of done. We get this is space is linear, lookup time is linear, lookup time constant, deletion time constant. This one is constant expected amortized. Except that we did all this using ideal hash function. Okay. So what to do? We want to avoid ideal hash function, but actually it turns out for this one, the usual trick, that is to use universal hashing family, is not enough. This is not enough anymore. And there is a paper that show how to attack this hash function if you use this. Just use universal hash family. But even if you don't see the attack, you can see from the analysis that it doesn't work. Because you see, when we analyze all of these things, we analyze some event that involve a path of length L. It's not about it's not just about choosing any two keys, whether they hash to the same place or not anymore. It's much more than that. It's much more than that simple, small collision property that we need. Here we analyze something much more complicated. So it turns out that log n wise independent is enough. If your hashing family is log n wise independent, that's enough. But yeah, log n wise independent is not that simple to construct, so it's not cool. There are papers showing that one simple hashing family called simple tabulation, that's enough. It's actually very simple, so you can look it up how it works. So that's very interesting. But I will not prove it here. Also, in this lecture, I put m equals 6n. Turns out that you can make it close to n. But which means that the total size of your space is still kind of more than double of your key, twice the number of your keys. But that's it's not clear how to go below this actually. But even to get this bound, it needs more complicated analysis. And also, you can also say that whenever you loop, whenever you do insertion and it loop more than log n step, you can also say that you're gonna rehash. Even if you say that it still won't rehash too many times. And this is why because of this log n thing that you want it to look more than log n anyways. That's why a log n wise independent is enough. But yeah, this is beyond the scope of this lecture. One thing I want to mention is that you also can remove expectation here. The insertion time can be just constant amortized with high probability. Yeah, there are some lecture notes about this you can look up, but yeah, I won't do this in class. And yeah, this one is a nice in practice too, so it's a cool one. Yeah. Okay, so what I want to finish with is just to leave you with to let you know one big open problem in this area. So okay, in this whole week, we spend some time to talk about dictionary with constant update and query time. And they are randomized, right? And that basically shows the power of randomization. But the big question is, can you do this deterministically? No one knows how to do this. No one can prove the hardness. So this is a question that is asked by Mihai Prasascu. So he's one of the most amazing guys in the area of data structure. Except that his work really inspired me in many directions. So he's a really cool guy. Except that he died in a really young age, so which is sad. But yeah, so until now we don't really understand the power of randomization clearly. We want to say that you cannot get this constant update and query time in constant time. We still don't know how to prove this. So next week we're gonna see more power of randomization. Is a streaming setting. So the setting is imagine that you are a router. There is a huge stream of information going through you. You are just a router. You don't have much space, tiny space. How can you even get some useful information out of this stream of information? So this is a setting where you can do something nicely using randomization, and you cannot do it without randomization. Okay, so that's it for today. See you next class.